going to start the lecture on nanotechnology in chemical engineering. Today we will discuss about the material characterizations of XPS. So, in our previous class already have discussed about the X-ray diffraction patterns. So, today we will discuss about the XPS, basics about the XPS, key principles and concept of the XPS and instrument details and examples. Few examples will consider means materials that will synthesized or that already have discussed. So, that materials will take, and then with the help of XPS how we can analyze different metals or ion compositions are present. So, that we will discuss. So, here is the XPS, X-ray photoelectron spectroscopy. So, the instruments is here. So, initially we have discussed that X-ray diffractions and X-ray photoelectron spectroscopy both are powerful surface characterization techniques. So, however, they provide different type of informations, or we can say that both are complementary to each other. So, from the X-ray diffraction spectroscopy we can get the crystalline structure of that materials we have or we have prepared. So, crystalline phases we can analyze with the help of X-ray diffraction patterns, and once we do XPS analysis, so it would gives us the elemental compositions and chemical state of the sample surface. So, same materials but different type of informations we can get with the help of these two specific characterizations. With the help of X-ray diffractions we can get crystalline structure, and with the help of XPS we can analyze chemical compositions or elemental compositions and chemical state of that particular metals or metal ion present in that particular materials we can get. So, I said already that X-ray can give you the crystal structures or phase compositions that is present in that particular materials we have prepared, and it with the help of X-ray diffractions there is some limitations, means up to 10 micrometers, that is the bulk of that particular materials, up to means bulk surface depth up to 10 micrometers we can go and we can get the X-ray diffractions patterns of that particular materials, and that particular properties we can identify, we can measure. Where in case of the XPS, that it was actually we can say that electron spectroscopy for chemical analysis. So, we said that the materials having different elements and its different states, chemical states also, means suppose we have a copper. So, copper's metals that is present in a chemicals or nanomaterials that we have. So, it may be two different oxidation state, copper plus 2 oxidation state, copper plus 1 oxidation state. So, both the metals oxidation state is present in that particular metals, but how much quantity, means quantifications of each ions is present in that particular materials we can measure with the help of XPS. So, this actually surface sample surface means chemical state that is present, or chemical means particular elements present, so that we can means oxidation state is present of that particular elements we can get with this particular characterizations. So, this is sample surface property we can get. So, up to 1 to 5 nanometers within that depth we can get that sample property. So, it is very sensitive, surface sensitive techniques. So, in instrumentation, so in this particular XPS, so components means instruments. So, that is the source of X-ray that is used. Also, a vacuum, high vacuum, ultra high vacuum chamber is required, and an electrons energy or kinetic energy analyzers that is present in that particular equipments. Some magnetic field shielding is there, electron detectors is there, and a set of stage manipulator is there. So, sample chamber is there where we can place that sample. So, here that schematic is showing here. So, sample chamber, sample source, detectors, X-ray source, these are the schematics is showing. So, here's the X-ray, how does it work actually? So, X-ray is based on the photoelectron effect. So, when we means fall a X-ray over a particular material, so then there is a possibility of electrons eject from that particular materials. So, means that electrons must have a kinetic energy. So, the kinetic energy of the ejected electrons, that is means moving from that, means when X-ray is falling over that material, so then electrons will be ejected from that materials, and that electrons ejected electrons kinetic energy we can measure with that help of this XPS instruments. So, basically these equipments measure the kinetic energy at the same time. So, when the X-ray interacted with the core electrons of that metals or the materials is present, so there is some binding energy is also present. So, binding energy means, so the energy requires to remove the electrons from the core of that particular materials. So here you can see, so here's this is the nucleus and this is the cores, different levels of electrons that is present. So here let's say X-ray that is falling over the K cells. So here these electrons will be move out and this is electrons coming out from that core, and see here some holes will be created. So after that, so there is an interaction, means here depending upon this energy, so that particular atoms, the electrons means that would coming out from this depending upon that amount of the energy that is present in that particular X-ray. Okay. So here's the orbitals that is present are closer to the nucleus having higher binding energy. So as a result, it having low kinetic energy also. So these electrons, whatever that is in the cores present, so with the help of X-ray, if we interact with that particular electrons and then it would move, so it's having, it's requires higher, it's must having higher binding energy. Also that electrons will moves with the low kinetic energy. So here's this kinetic energy or binding energy of that material or the electrons. So we can measure with the help of this X-ray 40 electron spectroscopy, and we can analyze to which particular type of metal ions are present in that particular sample. So here's the total energy we can express in terms of binding energy to remove that electron from that core, and when that electrons will move, then it has a kinetic energy. So total energy equals to binding energy to remove that electrons, means K cell, suppose that electrons is there, if we want to remove, so then the specific amount of energy is required, that is called actually binding energy, and then it would move say specific velocity. So then that is the kinetic energy. So total energy photon electrons and photon energy, that is equals to binding energy as well as kinetic energy. Apart from that, in case of the solids there is work functions, so that is expressed in terms of phi. So total energy equals to H equals to binding energy, kinetic energy and work functions of that particular solid that is we are analyzing. So that is required to get electrons that would be emitted from that particular materials. Okay, so here's in case of the analyzers, kinetics energy is there and work functions is there for analyzers, and here's the samples of the materials we have. So it has also kinetic energy and binding energy and work functions is there. So in case of the samples, so this is actually Fermi level. So in case of materials and analyzers, with the help of Fermi levels, so here the core, so this is the core electrons or core electrons level that is closer to the nucleus. So whence both analyzers and materials, this is the Fermi level energy that is aligned, and after that, so from there so we can find out the binding energy that is required actually, means with the help of equipments actually. So the binding energy we can measure or kinetic energy, and with the help of these XPS analyzers. Okay, so then we can get is what type of particular specific ions is present in that particular materials, we can easily analyze with the help of that. So here means with the XPS, so we can get surface spectra. So this type of spectra we can get here. X axis we are using binding energy and y axis the intensity of that. So in surface spectra you can see here one example we are showing. So here's this is our materials we are present: irons, manganese, oxygens, magnesiums, alumina. These are the 5 elements are present in that particular materials, and once we place that inside of that XPS equipments, and we can get this type of surface spectra. Okay, so at different locations, so you can see different peaks are present. So here's irons, oxygens, oxygen 1s, carbon 1s is present, manganese also present. So here's alumina. These are the peak we are getting at different locations, depending means upon that elements are present in that particular samples. So once we get surface spectra, so with the help of some software, so we can against individual metals and binding energy within that particular, suppose these irons that may be present in +2 oxidation state or +3 oxidation state. Manganese also maybe different oxidation state is present in that particular materials. So here's which particular specific metals presents oxidation state is present and what percentage is present, means quantitatively also we can analyze with the help of this spectra. So here's when here in XPS spin orbit coupling, that is very important. So here's in spin orbit coupling, so let's say s orbitals is there, p orbitals, d orbital or f orbital, depending upon that elements or the metals we have or the materials that particular specific metals is present, depending upon theirs the splitting of that particular orbital. So in case of the s, so here's actually the spin orbit coupling j, that is expressed in terms of l and s. L is this quantum numbers and s is the spin quantum number. So if we add them, so then either it is plus half or minus half, and this L we can get depending upon the orbitals. L equals to 0, 1, 2, 3, depending upon if it is S, then this L equals to 0, if it is p orbital then L equals to 1, if it is d orbital L equals to 2, and f equals to f orbitals L equals to 3. So if we add, then we can get J. So that is the orbitals coupling. So either for s orbital J equals to half. So electrons, number of electrons in s orbital should be 2, and in case of the p, j equals to, we can get 2j plus 1. So here's degeneracy, actually peak ratio of the doublet. So this j equals to 3 by 2 depending upon L and S. So L equals to 0 plus equals to L plus S. Here L equals to, if we put 0 plus half, or then so we can get half, or j equals to L equals to, for s orbitals it would be half, and for s orbitals j equals to half, that we are getting. So 2 electrons will be remains over there, and in case of the p orbitals j equals to L equals to 1 and s equals to plus half or minus half. So then it would be 3 by 2 or 1 minus half, so that would be 1 by 2. So j equals to 3 by 2 or 1 by 2. So this way orbitals coupling should be there, and then the total electrons in p orbitals is 6 electrons, that would be distributed this way 4:2. So then the peak ratio would be 2:1. In case of the similarly d orbitals also 5 by 2 and 3 by 2 we are getting j orbital coupling, and so the electrons will be distributed like this, and the ratio would be this 6 by 4 equals to 3 by 2 or 4 by 2 equals to 2 by 2:1. So here's now the surface spectra we are getting from the materials we are using or analyze with the help of XPS. So XPS software is there for a specific equipment, that is multi-pack you can say. So then this is the raw spectra we can get. So from there first we have to identify where carbon 1s is present. Okay, CS, this is carbon 1s. So that would be the actually carbon shift that is required, that is standard actually. With the help of that, so other metals, metal oxide or components are present, so that we can get. So first we have to smooth the spectrums, that whatever we have get with the help of the softwares, and after that so different metals I said present. Let's say here's manganese is present, iron is present, so oxygen is also present. So if we want to analyze, let's say here's manganese 2p, that manganese comes 662 635 electron volts within that range. So manganese that is coming within that range binding energy. Okay, so here's in manganese, so that may be Mn2p 3 by 2 lower binding energy, or Mn2p half, that is higher binding energy. And here the manganese may be present Mn plus 2 or Mn plus 3, two different oxidation states of metals may be present. Okay, so here's once we look that spectra, means surface spectra, and after that within that particular range, so 662 6, I said within that particular range we have to enlarge or magnify. So then we can get, so within that manganese 2p half, manganese 2p 3 by 2. So these two peaks we can get. This is raw spectra that we are getting. So okay, so after that we have to do the deconvolutions or deconvolutes, means new peaks we have to get with the help of that software. So here's deconvoluted spectra that we are getting. So here's initially it was this black spectra or red spectra, you can see. So after that, the deconvoluted spectra we can get with the help of the software. So there's you can get one pink color, another one this green color. So these two are two different oxidation states of that metal. So that is present manganese +3 oxidation state or +2 oxidation state. So in case of the manganese 2p half, so there also the similarly deconvoluted spectra or peaks we can get of that specifics two different metals, metal manganese +3 and manganese +2 also we can get here also. So once we analyze that deconvoluted spectra of these particular metals, so then area under the curves we can get, area for that specific spectra peaks we can get, and by that way you can quantify how much quantity of that total manganese present, and up to out of that each metal science, that is manganese +3 or manganese +2, two different metal science are present in this particular samples. So from area under the curves we can get how much percentage of this and this individual metal science are present in that particular samples. So here I'm showing here similarly, so two major peaks whatever the we are getting. So 2p 3 by 2s, they are manganese +3 and manganese +2 both are present. So here another spectra that I'm showing, so that is in case of fresh samples and used samples, means the same materials once used for specific applications. After that the used materials also we have done the XPS analysis, and there some specific changes are observed in terms of intensity of these two different metal ions I said present. So intensity means area under the curves of these ions would be changes when it is used. So based on that also we can say fresh samples means initially before applications, means specific applications we have used that materials, means how much quantity of individuals ions are present, and after reactions or any applications if we also again quantify each ions are present. So then we can say that during that specific applications maybe one ions converted into another's ions, so maybe oxidations or reactions might be taking place and changes are also there, so that we can get with the help of this deconvoluted spectra of that particular materials or that particular specific ion changes during that specific reactions or applications where we are using these materials that we have prepared. Next is the interpretations of iron 2p. So iron's 2p, that also I said is specific range of binding energy, means here we have split up from the surface spectra. So here 7052, this 740s I think, so within that 735s we have considered. So iron, in case of the irons also iron 2p half, iron 3p 2p 3 by 2 also we can get. This is the main survey spectra, and then we deconvolute it. Once we deconvolute it we can get this violet peak and another pink peak. So one is iron +3, another is iron +2 oxidation states. So once having higher oxidation states, so requires higher binding energy. So that is why this one is coming higher binding energy and iron +2 lower binding energy. So here's the area, similarly area under the curves of this deconvoluted spectra we can get an amount of iron +2, amount of iron +3 is present. So we can means quantify, means individuals ions we can detect, at the same times concentrations or quantity of individuals metal ions are present in that particular samples we can analyze. So at the same time another satellite peak is also is present, sometimes that is comes in few samples you can get this type of means satellite peaks we can get. Apart from these two different oxidation states, these two peaks, another peak is also present that you can observe, okay, in few materials. Next is the oxygens 1s, that is coming in the surface spectra. So in that particular region, so means 536 to 524, within that particular specific range, so there's we can get oxygens 1s spectra in the surface spectra. This is the surface spectra. and after that we can get deconvoluted spectra with the help of the software. So here three different type of oxygens that is present in that particular materials. So that may be lattice oxygens, maybe surface hydroxyls group presents, or maybe two different type of oxides here we are getting. So metal oxides and surface hydroxyls means when the materials we have taken, that is the metal oxides, so therefore lattice oxygens in presence. At the same time some moistures or waters also may get adsorbed over the surface of that material. So then therefore this type of oxygens or another peaks also we can get. So we can say that that may be due to the hydroxyls groups are present in that particular materials that we have prepared. Okay, so here's another examples that I am showing. So here's analysis of the surface picture of that materials. Here we have taken a materials that was prepared made of copper, manganese, phosphorus, oxygens, also alumina and oxygens. These are the components are present. So here three different materials we have taken, 1, 2 and 3. All three different materials having same quantity of copper, manganese, phosphorus, oxygen, alumina, oxygen. So these are the present same quantity. So but preparations was different. Preparations methods of preparation of the three materials was methods 1, method 2 and method 3 was used to prepare these three different materials. And then we have gets this is the surface spectra of three different materials. Materials 1 surface spectra, materials 2, materials 3. So here's almost all these peaks look similar like. So here's carbon 1s spectra is coming here. From the surface spectra you can see close to 300, so 280 I think. So that we are getting carbon spectra, and after that with respect to that we can get copper 2p half, copper 3 by 2 splitting, manganese we are getting, oxygen 1s we are getting, phosphorus, alumina also we are present here in this particular. So first we get 24 electrons volt, there's we are getting carbon 1s peak, that is as we can consider as a calibrations reference I said. Then oxygens, and then copper 2p half and copper 3 by 2 peaks, and then alumina and phosphorus at different locations we can get. So now we can analyze individuals metals are present, coppers, manganese. So within that range we can means I said the copper interpretations means here's in the surface spectra, here we can get copper. So within this particular range, so we are against enlarging and we can get deconvoluted spectra. Okay, so here's means we are interpreting that coppers, that metals is present, that may be either +2 oxidation state or maybe +1 oxidation state, both may be present but different quantity. So individual metal science we can detect or we can identify and quantify also we can do. So how much this and this species are present in that particular samples. So copper +2 that will be split up into copper 2p half and copper 2p 3 by 2 peaks. Similarly copper +1s also would be split up as copper 2p half and copper 2p 3 by 2 peaks. So here's the deconvoluted spectra we are getting with the help of the surface spectra. So then this is copper 2p 3 by 2, this is copper half 1 by 2. So here's when deconvoluted, one is the violet, another one is the pink. Both peaks will come from the surface spectra to deconvoluted spectra. So here's this violet color spectra, that is copper +2 oxidation state. This pink colors, that is deconvoluted peak is coming, that is copper +1. Similarly here also copper 2p half also, they are also deconvoluted peak and spectra that we get for different metal science are present in that particular sample. At the same time satellite peak is also we are getting some satellite peaks also present in these particular samples. Okay, so I said already this peak correspond to different oxidation states present of that copper present. Okay, similarly manganese also we can get manganese metals is present, that would be splitted up in terms of this manganese 2p half and manganese 2p 3 by 2. Here's manganese 2p half, that would be splitted up three different metal oxidation states. So metal manganese +2 +3 +4 oxidation state. So similarly this also would be splitted up manganese plus 4, manganese plus 3, oxidation state on manganese plus 2. So manganese 2p 3 by 2, that also split up, and 3 different locations that we'll discuss after deconvolution we can get. So this is the surface spectra and these two are deconvoluted spectra. So here's deconvoluted spectra, so 3 different deconvoluted spectra you can get. So here's this particular locations means binding energy 644.4 electron volts, manganese plus for oxidation state. So you can get this, and then 642 electrons volt, that is manganese plus 3 oxidation state, and then manganese plus 2 oxidation state 641. 3 different locations in the deconvoluted spectra we can get 3 different type of metal ions are present in that particular samples. Okay, so here's just particularly manganese 2p 3 by 2 we have discussed. Similarly manganese 2p half also, that survey spectra, survey peak we can get, and after the deconvolutions of this manganese 2p half we can get 3 different metal ions are present there also. Okay, similarly interpretations of oxygens 1s, interpretations of phosphorus 2p, that also we can get a specific survey peak and that we can analyze. Okay, so oxygens, this was the survey peak from the survey spectra, and after that deconvoluted, so one is pink color, another is violet, another is brown color. So 3 different peaks we can get and 3 different intensity also. So peak area under the curves is not same in 3 different deconvoluted peak or spectra. So individuals metals, these oxygens, lattice oxygens or adsorbed oxygen or surface hydroxyls present at different quantity in this particular samples. Similarly also the quantifications if you want to do by considering or measuring the area under the curves for oxygen 1s of this particular samples, it would be different. Similarly these samples also it would be different. Small means sample to sample, if you analyze this particular deconvoluted spectra or peak specific, this if you want to get lattice oxygens is present in this particular material, this materials and this materials, specific lattice oxygens, that quantity also would be different. Okay, so here similarly for in case of the phosphorus also interpretations we can say different type of phosphorus oxides are present. So now quantitative analysis with the help of XPS means I said copper, manganese and oxygens are present. 3 different key components or metals are present in that particular materials. Once we get the XPS spectra, so then with the help of the softwares we can smooth that particular survey spectra. First we can get survey spectra, then we can smooth the spectra, and then we can do the deconvolutions of the spectra. Okay, so then once we get deconvolution spectra, then individuals metals are present in terms of specific metal oxides, so we can quantify with the help of that software's area under the curves. Let's say I said copper is present, percentage of copper is present, percentage of manganese is present, or percentage of oxygen is content, that is the absolute contents or quantity for a specific sample. Let's say these samples we are saying, so oxygen's quantity is 70.1 percentage absolute quantity. With the help of the surface spectra we can get absolute quantity of copper is present 1%, 1.8%, and absolute quantity of manganese is present 2.99 percentage. Okay, so total amount of oxygen is present this, manganese is present, and copper is present this. So now from percentage of absolute quantity with the help of surface spectra we have getting this. After that the spectra we are deconvoluted peak we are getting. So that would gives, since copper is present, copper plus 2 oxidation state, copper plus oxidation state, so total copper is present this, copper plus 2 with the help of the deconvoluted spectra we can get copper plus 2 with respect to the total copper. Copper plus 2 by total copper is this percentage, copper plus 1 divided by total coppers is this. So relative contents of this ions, specific ions, either copper plus 2 or copper plus is present. So here copper plus 1 is more than copper plus 2, means approximate 80% copper plus 1 is present and 20% copper plus 2 is present in that particular sample. Okay, similarly, manganese relative quantity of individuals metals ions are present in that particular samples. I said in that materials manganese plus 4 plus 3 plus 2, three different metals ions are present in that samples. So absolute quantity that was 2.998% are present, that manganese. So means after that, with the help of deconvoluted peaks area under the curves, we can get manganese plus 4 oxidation state is 41%, manganese plus 3 36%, and manganese plus 2 22%. So this is the individual metal ions are present in that particular samples is 41%, 36%, 22%. So by that way means we can identify and means quantify relative quantity of different metal ions are present in that specific samples. Whatever the materials, that may be manganese, coppers. Here we have taken that samples present copper and manganese and oxygens also. Even I said oxygens was 71%, 70.1% is present absolute quantity with the help of surface spectra. And deconvoluted spectra oxygens also we can say that lattice oxygen that is present 46%, adsorbs oxygen that is present 51% approximate, and surface hydroxyl groups is also present in that sample. So hydroxyls is present 0.018 percentage. So different metal oxides are different metals, oxygens and different types of oxygens that is present relative quantity. Also with the help of surface spectra we can converted spectra we can find out relative quantity of oxygens present. Okay, so thank you. So today is up to this. So we have learned XPS means about the instruments, XPS instruments, how does it work, and then surface spectra of a specific samples, and then deconvoluted spectra how we can get with the help of substrates, and then the deconvoluted spectra we can picks what are the different metals ions are present, means at that particular samples we can quantify, that we have discussed. So I hope with this, so for our specific samples that is present or we can prepare, that we can analyze with the help of XPS. So that is very useful characterization techniques if we particularly quantify a specific metal ions are present in that samples. Okay, so that is very useful. So thank you. Today is up to this.